We were just talking about the forward-backward algorithm for the hidden Markov model, and we saw how to get the distribution on like a given zk, given all the x's, we wanted to do a forward part and a backward part. And here we're gonna talk about the forward part. So this is a great example of dynamic programming. And this both the forward and backward algorithms are extremely simple. But for some reason, most expositions of them are rather complicated. So I think, I'd like to show you how you can just very simply understand what this algorithm is doing. And it all boils down to there's one trick. It's the Leatherman trick for Markov chains, and you can use it over and over again in so many different ways. So you'll see what that trick is in this video. So the goal for the forward algorithm that we mentioned before is that we want to compute these joint distributions on zk and x1 through k, where x1 through k is the vector, is this vector. So this is what we want for all k and all zk. We're given the x's. And so let's take a look at it. Let's just write that down and start working with it and see what we get. So let's just write that down. Let me get rid of this. I think we're going to want some space over there. So what do we know? We know the transition probabilities. We're assuming we know all the parameters, transition probabilities and emission probabilities and so on. So how can we introduce those into here? Well, maybe we can get some transition probabilities. If we sum over, here we only have zk. Maybe if we get zk and zk minus 1 in there also, then we can somehow introduce the parameter. So let's sum over the possible values of zk minus 1. And here I'm assuming that the z's take values in the set 1 through m. So this is summing over all those possible values. And of course, this is just by the marginalization property. We just introduced zk minus 1. And let me make a new line. I think we're going to need some space for this one. So we have the sum. And now I'd like to factor this in order to use those things that we know. So we want to use the transition probabilities and so on and so forth. So first we have this. So what do we have here in this expression? We have x1 through k. That's all this part here. And we have zk minus 1 and we have zk. So thinking about how this distribution factors, this thing factors, well, this part's probably going to pop off right here, right? We're going to have xk given zk. It's going to be conditionally independent. Maybe we can check that formally. So, but for now, let's write all the others. zk minus 1 and x1 up to k minus 1 times the probability of, so we have this stuff left still. So let's put, what should we put next? Well, zk is the next natural thing. Zk, given this other stuff, it's going to be conditionally independent of this other stuff given zk minus 1. So we're going to get a transition probability here. If you don't see that right away, then we'll check that in a second. And given x1 through k minus 1 times the probability, what's left? Zk minus 1, whoops, zk minus 1, given this one, x1 to k minus 1, and then this is the only thing left. Probability of x1 to k minus 1. Actually, on second thought, let's keep those last two together because they look a lot like this. Let's keep those together because that's going to look like this, but in the case of when k is replaced by k minus 1. Okay, so the idea here is that we're trying to take this expression. So the trick that I'm referring to, the Leatherman trick, sort of all-in-one trick for Markov chains, is that you take this thing and then you marginalize over sort of one step back. So here we had zk, marginalize over sort of one step back or one step forward, as the case may be, and then factor things into, using the Markov properties that you have. So you're going to factor things for that one step, and then you get a recursion for the thing that you were trying to compute. So let's check that. Let's apply those Markov properties. Let me switch colors here. Let's apply those Markov properties. So here I mentioned that, or I claim now that xk is conditionally independent of zk minus 1 and x1 through k minus 1 given zk. So if we condition on this guy, I claim that this is conditionally independent of all of this stuff here. And why is that? Well, if you write, if we use d-separation, maybe I'll put a red here, it always has to go through this blocked path here. The path, any path from here to one of these, has to go through here, and this is conditioned on. So it's blocked at this tail. So we can write this. Boom, we can get rid of those. So this just becomes this guy, xk given zk given zk. Actually, let me undo my red dot there. I'll just put it here. And now, how about this one? Well, I'd like to say that zk is conditionally independent of x1 through k minus 1 given zk minus 1. So let's uncondition on zk, and let's condition on zk minus 1. Now what happens? So I'd like to say that this is conditionally independent. This is conditionally independent of this given this guy. And we have a tail here at the thing which is being conditioned on. And so any path from here to one of these is going to have to go through that, right? So it's blocked. So these are d-separated and therefore conditionally independent given zk minus 1. So we also have this. Boom. So that's the step. So the first step was we marginalized here. We expanded this out. Then the next step was we applied the conditional independence properties, the beautiful conditional independence properties afforded to us by our very nice tree structure in the graphical model. And those were the Markov properties for this model. And now what do we have? Now we are in very good shape because this we know. This is known. This is just the emission probability, right? Probability of xk given zk. That's what we have assumed is known. It's the emission probability. Emission probabilities. And these are known because these are just the transition probabilities. And we are assuming that we know those. And this, so let's give this last part, let's give this a name, and this first part, a name. Let's call this alpha k zk. We're assuming that we're given some x's, so the x's are sort of fixed. So if we fix, we fix here, fix the x's, and the z's are the only thing that are sort of variable. So this is a function of zk and k. It also depends on k, of course. And so this, under that definition, is alpha k minus 1 of zk minus 1. So it depends on the value that zk minus 1 takes here. So let's write down what we found. Let's write this nice little recursion. We get a recursion formula. Sum over zk minus 1 from 1 to m. The transition, or rather the emission probability, xk given zk. The transition probability, zk given zk minus 1. And the thing that we are recursing on, alpha k minus 1 of zk minus 1. So that's nice. And we can do this for any, so as long as k is 2 or more, then everything here makes sense as long as k is 2 or more. So this is for k equals 2 up through n. This formula applies. So this is a recursion in these alphas. So that if that's for k from 2 to for 2 from 1 to n, when k equals 2, what is alpha 1? What is alpha 1? Let's look at what alpha 1 is. Well, alpha 1 of z1, by definition, here, the definition is the probability of z1 and x1 through 1, which is just x1. And let's factor this. So we want to factor this in terms of things that we know. So what do we know? We know emission probabilities, we know transition probabilities, and all that good stuff. So we can factor this. And we know the initial distribution. We can factor it into the initial distribution times the emission probability of x1 given z1. And each of these is known, right? This is the initial. This is the initial distribution, so it's known. And this is the emission probabilities. Emission probability, so this is known. So this is sort of an initialization step, if you will. Get rid of those. And these two equations allow us to compute the alphas. So we can compute. So this gives us a sort of recursion to compute, starting with alpha 1, we initialize, and then we get alpha 2 using this formula, alpha 3, all the way up to alpha n. We can compute those. And once we have all of these alphas, that was exactly what we wanted. We wanted to get that. Those were the quantities that we were interested in. So that gives us these probabilities for all k from 1 to n. And that's it. It's just super simple. I mean, basically, 2 steps. You expand this out in terms of the sum here. You apply the conditional independence properties. That's it. That is all the forward algorithm is. That's all there is to it. It's stunningly simple. It's amazing. And the amazing thing is, so okay, not only can we compute these, the awesome thing is, here's the awesome thing. This requires, how much time does this require? Let's think about computational complexity. So we have to, what do we have to do? We have to compute this sum for a given zk, we have to compute this sum. And we have to do some multiplications, but all that's just a constant. That just falls out. That's a constant. So the order of the computation is the sum, which is m for a given zk. So it's O, so it's OM, it's actually theta, capital theta of m for each zk. And how many zk's are there? Well, there are m. So we have to multiply that by m. So it's m squared for each k, right? We have to do this once, we have to do this sum once for each value of zk in order to get this whole, this whole function alpha k for all the possible values of zk. But then we have to do it once for each, we have to do that whole process once for each possible value of k. And k goes from 1 to m. So this is, and this, so there's n times. So this is, well, it's, in particular, it's big O of nm squared. And in fact, it's theta, big theta of nm squared. So this is the computational complexity of this algorithm. Okay, I'm out of time in this video, but let me come back and make some final remarks on the forward algorithm.